Hey, so one of the things I didn't grab from my office when I was scrounging for all my materials to teach from home was my molecular model kit and my hybrid orbital model kit. Now, I couldn't replace the hybrid orbital model kit because those buddies are hard to find and stupid expensive, but I did order a model kit just showing shapes off of Amazon and it just showed up today. So I'm going to do a quick recap of the valence shell electron pair repulsion theory, focusing on just the electron domain geometries and molecular shapes with models so you can actually see kind of what they look like. So I'm following the electron domain geometry, molecular shape, and hybridization worksheet thingy. It's just I'm going to have models to show you now. The models aren't very large, but they're better than no models. And I put those simulation things up there, hopefully to help, but those were still on a computer screen. So for me, and this is still gonna be on a computer screen. So I don't know, it makes me feel better because I'm holding the models, but you guys, we'll just see. Also, it's getting ready to start thunderstorming, so hopefully that's not too loud and we don't lose power or anything like that. Okay, so I'm gonna make me smaller for a minute. Hopefully I'm smaller. We're just going to start at the top at 2 electron domains and work our way down. So I'm going to draw a Lewis structure that has 2 electron domains. So, okay. So B, beryllium, and 2 hydrogens. Beryllium is one of the central atoms that violates the octet rule by having less than 8 around it. It always has 2 bonds or 4 electrons. So it has 2 electron domains because it has 2 single bonds. Just again, a reminder, electron domains, one pair of dots is an electron domain. A single bond, ooh, smiley face, is an electron domain. A double bond is an electron domain, and a triple bond all count as 1 electron domain. Yep, that's how it's going to be. Okay, so we have 1, 2 electron domains. So according to our worksheet, the electron domain geometry is linear, and it has bond angles of 180 degrees, and its molecular shape is also linear. So the middle silver guy would be the beryllium, and the 2 purples would be the hydrogen. So it's literally just a straight line. So the bond angle is 180 degrees because it's a straight line. Okay, so as long as you have 2 electron domains, this is the only option. Okay, I'm gonna make me small again. Okay, so let's go to 3 electron domains. So the example, really, I'm not talking to you guys, I'm talking to my computer. Probably tired of me talking to my computer. This one has 3 electron domains because it has 3 single bonds. So 3 electron domains, according to our worksheet, is trigonoplanar electron domain geometry. And if all 3 electron domains are bond, it's trigonoplanar molecular shape. So this is trigonoplanar. So central atom would be the boron, and then hydrogen, hydrogen, hydrogen. This buddy's flat. Okay, so it's like if I just drew a circle and divided it up kind of like a peace sign. That's pretty much what's happening. Our bond angles are 120 degrees between all of them because they're evenly divided within a circle. And again, it's flat. Okay, so technically, I guess, well, there's no 180 bond angle, but like, it's flat. Okay, so there we go. If I had something like, this buddy. So the nitrogen, if we're counting electron domains, has 1, 2, 3 electron domains. So it has 3 electron domains. So its electron domain geometry is trigonoplanar. Bam. But in real life, one of them will be a double bond, one of them will be a single bond, and one of them will be a lone pair. And since it's a lone pair, there's no atom out here. So there's no like outside of this. So in real life, we wouldn't see that lone pair. This is all we'd see. There is something there. They're lone pair electrons. This model kit came with these little paddle things, which represent the electrons. Okay, so what we'd really see is this. So it's like trigonoplanar, just missing an arm. Okay, so its molecular shape is now called bent. It's in the electron domain geometry of trigonoplanar, but its molecular shape is bent. And again, it's invisible, or if we want to put this on there, that's what's happening. So since those lone pair electrons are floating around up there and they have all this freedom because they're not stuck within a bond, they have this freedom to move. I can't do it with this model kit, but these bonds are going to kind of like, they're going to shy away. They're going to be afraid of, they're going to move away from those electrons. They're not actually afraid. They're repelled by them because they're electrons and these lines represent electrons. So that's why the bond angle here becomes less than 120 degrees, because they get closer together to get away from those lone pair electrons. Okay. There we go. So oh, and I ignored the hybridization, but the hybridization, the model kits don't super help you with that. CH4 is the standard 4-electron domain, all 4 bond situation. I don't know if we can see the yellow, but I'm going with that. So it has 4 electron domains. So according to our handout, it's tetrahedral electron domain geometry. Tetrahedral is the first one that's not flat. Okay, so tetrahedral is fully in 3 dimensions. So the way the tetrahedral shape looks, there's one straight up and one straight over. Those would be flat to each other. But then there's one going out towards you and one going away from you. So when we twirl it, it's like a top with 3 legs and one sticking up. Now if I rotate it, looks exactly the same. If I rotate it, looks exactly the same. If I rotate it, looks exactly the same. So one up, one straight over, one forward, one back. So one up, one over, one forward, one back. That didn't help at all, but okay. So that would be tetrahedral. The bond angle here is 109.5 between all of them. And again, it's weird because this is truly in 3 dimensions. So it's not flat. We're not just dividing up a circle. It's bigger than that. Okay, so let's move on to something else with 4 electron domains. There. But where they're not all, oh, this is the other standard one. No. Okay, let's change colors. Green. Nitrogen, hydrogen, hydrogen, hydrogen. So again, you can draw your Lewis structures however you want, but you need to be able to visualize these shapes, especially when we're talking about polarity. Okay, so boop, nope, boop. Okay, so nitrogen, can I move? Nope, I can't do that. All right, so nitrogen with 3 hydrogens and 1 lone pair counts as 4 electron domains. So its electron domain geometry is tetrahedral. But again, we only have 3 atoms. There's one spot that's just empty. Okay? It still stays in the same shape, but it's invisible. So I'm going to take off this atom, and this is the shape that I get. Now, just to prove that it doesn't matter which one I take off, let's go with the lone pairs are right here. Take that one off. Make the shape. It's the same. Okay, so this has an electron domain geometry of tetrahedral because it has 4 electron domains. 3 of them are bonds, 1 of them is a lone pair. So one arm is invisible. That makes it trigonal pyramid. Now that is different than trigonal planar. Sorry, I'm missing an arm for trigonal planar. Trigonal planar was the 3 electron domain geometry. There's only 3 electron domains. Okay. Trigonal pyramid. These are not the same. Okay. This one, the trigonal planar has 120 degree bond angle. Only happens when you have exactly 3 electron domains. When you have 4 electron domains, trigonal planar is not an option. Trigonal pyramid is, because if we were to cover these sides up, it would make like a pyramid. It's got 3 legs, okay? The bond angles are all going to be a little bit less than 109.5 because they're hiding from that lone pair electrons. Here, I'll put this guy on there. So it's going to be less than 109.5 because of that. Okay. If you're in this molecular shape, the molecule's polar. Like 100% of the time. If you're in this molecular shape, the molecule is polar. There's no way for these arrows to cancel themselves out. Okay. Oh, it's definitely raining outside. I don't know if you can hear the rain. Let's go with water. Pen. Maybe. 1, 2, 3, 4. So it has 4 electron domains. Here we go. 4 electron domains. So its electron domain geometry is tetrahedral. Okay. But only 2 of them are bonds and 2 of them are lone pairs. So I'm going to pull off 2 of them. There's something there. They're just invisible somethings. Okay. So I'm going to pick 2 of them. It was tetrahedral. Now it looks like this, which is bent. It's the same name as in trigonal planar is bent, but the bond angle is different. When it's tetrahedral electron domain geometry, Molecular shape bent, the bond angle is less than 109.5. When you're trigonal planar, electron domain geometry, molecular shape bent, your bond angle is 120. So I don't know how well you can see the fact that these aren't the same angles. If I try to whatever, they're not the same angles. You're just gonna have to believe me because I'm really bad at this. So one common mistake is someone will tell me for water that they have the electron domain geometry of tetrahedral and the molecular shape of linear. Dude, there's no way to take this electron domain geometry and make a straight line with any 3 atoms. You choose any 3 atoms and it can't be a straight line. So you have to stay in your lane. Like if you're in the 4 electron domain geometry page, you can't flip off of this page. If you have 4 electron domain geometries, you live on this page. You have to choose one of these options. Okay. Let's go to the next one. 5, which is obviously the best because it's trigonal bipyramidal and it has seesaw and everything's wonderful about it. So let's do PH5. So we draw our Lewis structure, and I know I'm jumping, like I'm not counting my electrons like I'm supposed to, but guys, you can just believe me on this one. I've been doing this a while. You need to count your electrons when you draw your Lewis structure. But 5 electron domains is trigonal bipyramidal, which is the coolest one because we have 2 different types of atoms. We have axial atoms and we have equatorial atoms. The equatorial atoms are around the middle, like the equator. The axial atoms are above and below, like it's on an axis. Okay, so here's what it looks like. It looks, basically, it's the combination of a linear shape. So if you look gray to purple to gray, that looks linear. Okay, so it's like I took the linear shape, and then if I look down, if I look at just green, purple, green, purple, green, purple, that looks like trigonal planar. Because it is. So trigonal bipyramidal is a linear shape and a trigonal planar shape put together. So that's why we have so many weird bond angles. So bond angle between here and here, just like trigonal planar, it's 120. Okay, just like linear between here and here, it's 180, and that's the one I always forget to tell people. So I'm sorry, I don't think it's on the worksheet. You need to add it. It shows up in seesaw, but it doesn't show up in trigonal bipyramidal. But the silver atom to the silver atom is 180, and then the bond angle between the axial and the equatorial is a right angle. It's 90. Okay, so this one's weird, but it's cool, so it's worth it. There we go. I'm going to write H's because I don't want to put all the lone pair electrons. So SH4, not orange, 1, 2, 3, 4, 5 electron domains. But of those 5 electron domains, only 4 of them are bonds and 1 of them is a lone pair. So one of them is going to be invisible. Okay. So there's only one right answer to this. In which atom you can remove? Well, take that back. There's 3 right answers. But it has to come from the equatorial. Okay. Because the axial atom, it to its closest neighboring atom is a 90 degree. I know it has a 180 degree bond angle with its other axial atom, but it's got all these 3 atoms in the way. So that's 90 degrees is the farthest away it can get from another atom. But if we're looking at our equatorial atoms, they're 120 degrees away from each other. Remember these electrons that make everything repel? They need space. So the place that it can get the most space is in the equatorial spot. So the lone pair has to go in the equatorial spot. Any of the 3 in the equatorial. So this one, which, I mean, it looks like this, but it looks cooler when it's like this, like a seesaw. Okay, its bond angles, well, all 4 of these atoms are going to smush. Okay, so what's going to happen is the here to here bond angle is going to become greater than 180. It's not straight anymore because the atoms are smushing away. The here to here or here to here is going to be less than 90 because they're smushed, and that's going to be less than 120 because they're smushing. So those lone pair electrons are causing the rest of the atoms to condense. All right. I H lone pair 1, 2, 3, 4, 5 electron domains, so its electron domain geometry is absolutely trigonal bipyramidal because it has 5 electron domains, but its molecular shape, so again, here's the trigonal bipyramidal TBP because it's cool and has a nickname, but 2 of these equatorial spots are going to be invisible. So bam, bam. I don't care which 2 I take off. What I have left is this, which if we rotate it, looks like the capital letter T. So the very original name of T-shaped shows up. Now, there's 2 sets of lone pairs floating around up here. So these 3 atoms are still going to be smushed. So the bond angle is going to be greater than 180 between that and less than 90 between that. Okay. And if we get into a situation, did I do an example? I did. I guess xenon's probably my best central atom for this. Where I have 5 electron domains. 1, 2, 3, 4, 5 electron domains. So the electron domain geometry is trigonal bipyramidal. Okay. But only 2 of them are bonds and 3 of them are lone pairs. Well, the lone pairs have to go in the equatorial spots, so goodbye, goodbye, goodbye. What we're left with is the linear molecular shape, and this bond angle would be exactly 180 because there's electrons all the way around it, so it's being smushed on this side and it's being smushed on this side, so it's being smushed into a straight line. Okay, so the only bond angle left is the 180. And then our last scenario is 6 electron domains, which following the pattern should be like hexa something, but people don't let me make these decisions. So 1, 2, 3, 4, that's an H, 5, 6, oh, green, come on buddy, 1, 2, 3, 4, 5, 6, 6 electron domains. So it has the electron domain geometry of octahedral. Again, I wish it was hex something, but the 8 is coming from 8 sides. So if I were to put a side on this, 1, 2, 3, 4, sorry, can't, this, whatever. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 sides. So there is a reason, but it's a dumb reason. So it's octahedral electron domain geometry, and if it has all 6 bonds, it's octahedral molecular shape. And this one does not have axial and equatorial atoms because if we look, bond angle from here to here is 90 degrees. I'm going to rotate it. Bond angle from here to here is 90 degrees. Now I'm going to like look down this axis, like I'm looking down it. 90 degree, 90 degree, 90 degree, 90 degree, 90. They're all 90 degrees. All of these are the same. If I rotate it, I make the same thing. With trigonal bipyramidal, where'd you go? There, I took off. He's all naked. He doesn't have his equatorial atoms. This is with 5 electron domains. If I look at it like this, and then I rotate it, that's different. With this one, if I look at it like this, and then I rotate it, this is way harder than it should be holding models. It's not, it's the same. This one, no matter how I rotate it, comes up with the same shape. This one, there is a difference between the around the middle and the up and down, which is why trigonal bipyramidal's a weirdo. Okay, so when I run into something, now I'm making stuff up. We're gonna go with this molecule that doesn't exist, but you're just gonna bear with me. 1, 2, 3, 4, 5, 6 electron domains, but 5 of them are bonds and 1 of them is a lone pair. Pick one and make it invisible. Okay, so what we have is bond angle wise, we now have a 180 bond angle, but it's going to be greater than 180 because they're smushing. And then our bond angles are going to be less than 90. But the shape is called square pyramid because it would have 4 sides, but it would make a pyramid if we put sides on it. Okay, now if we, now I'm going to get super lazy. Have 6 electron domains, but 2 of them are lone pairs, Okay, it's electron domain geometry is octahedral. 2 of them are lone pairs, so I pick any one to put the first lone pair as. First lone pair there. Okay. Now, the other one, the other lone pair is going to come directly opposite it. Some of these electrons want to have all the freedom. So now this set has all the freedom over here, and this set has all the freedom over here. So this is square planar, because it's like the shape of a square, but it's flat. Okay, so the bond angles are going to be 90 and 180. And these will be perfect because it's being flattened from the top and flattened from the bottom, so it's stuck. Okay. And if we have 3 sets of lone pairs and 3 bonds, we get to T-shaped, just like we did the trigonal bipyramidal. And if we got to 4 sets of lone pairs and 2 bonds, we would get to linear, just like we did the trigonal bipyramidal. So I don't know if me having these models helped you at all. I wish I could hand them, like, here, take them from the computer. I can't do that. So I tried. I hope you guys are doing well, and let me know if you have questions. Bye.